Hi guys, my name's Gaz Roberts. It is currently the 4th of January 2026, and this is the first part of the build series for the UK rocket attempts on some of the smaller motors. Now, we're going to be using is a program called Open Rocket, which is open source software. It's readily downloadable from online. Just go to Google, type in Open Rocket, download the latest version, and then literally run the program. I think I'm up to date with the current version, which is 24.12. I believe off the top of my head it came out about January last year. July, sorry. Right, what I want to say before we start is that I'm not really into editing videos, writing scripts, so we're basically going to have a go at doing it live. Now, this program is very easy to use, but you can get some amazing results out of it. Simulations, you can get all the mass aerodynamics of your rocket. It makes life easy. To be fair, if this program wasn't come out, I know how I could work it out, but this program, again, like modern technology, just makes it that little bit easier and probably that bit more enjoyable for many people. Right, with a rocket, when you're building it in Open Rocket, you've got to start with the nose cone. So we'll open up a nose cone. As you can see along the bottom, we've got a ruler here. We can see the dimensions of the rocket, so it's 150 mil long, and which is the parameters that we can see here. Now, we're going to make these nose cones out of carbon fibre molds eventually, so we're going to aim for them to be about between an average of 1 and probably 1.2 mil. So we'll go on the excess and say it's 1.2 mil. Now, this is important because it's going to help calculate the weight of the nose, and which will eventually help with us get the stability of the rocket. What you've got over here where we can see materials, the program is very good now, so you can literally select what material you're making it out of, and it's got an average weight. So we're going to go for composites and carbon fibre. The base diameter, now the way that we're working out, or we know what the base diameter is that we're using on this program, is because we're building a minimum diameter rocket. Now, the rocket motor itself, and the ones that we're using in this series of rockets, is 18 mil diameter. So we're aiming to go for a 19 mil outer diameter, which will leave us a 0.5 mil wall on the rocket. So we want a base diameter of 19. Now, obviously, a long pointy nose would really help us to get the maximum altitude, but because we're going to be running a couple of electronic devices inside it, one for measuring the absolute altitude, which is called apogee, which is basically the top height that the rocket will hit, and the second one is a device that's basically stolen from drones. It detects movement of the rocket when it starts, and then when it doesn't detect movement, it starts panicking and beeping, which you can hear from fields away, basically, which is going to help us locate it. Because if we can't find the rocket and pull the computer out and read the altitude settings and pull the data off it, we have no way of proving that we have done the rocket. So we're going to shorten the nose down, and we're going to do it at 30 mil. So there we've got, and we've just got a standard O-gauge nose, 30 mil. It's estimating 2.5 grams. Now, what we also need is a way of fastening this to the rocket. So it's called a shoulder. So the shoulder diameter needs to be internal diameter of the tube, which we know is 18 mil because that's the size of the motor. Now, it only just needs to go inside the rocket because we're going to bond it in with epoxy. So we'll say 5 mil, and again it's going to be an average hopefully of about 1.2 mil. And we're doing the average weight more for the weight side of it. So that completed nose cone there is 3 grams. Now, after the nose cone, we need to select a body tube. Now, the body tube, once you click it, or just a quick one, why all these are coming up, these are standardized tubes that you can buy it. What I'm going to do now is tick this box because I don't need to see that because we're designing everything ourselves. So the tube has automatically picked up the diameter. It's got an inner diameter at the moment of 15. So what we're going to do is change the wall thickness to, oops, there we go, 0.5, which will put us to 18. Now, for reasons that it'll be a bit easier to explain later on, because we're minimum diameter, we're going to have to use two body tubes because we're going to use the motor to couple it. So just to make life things easier on the screen, we're just going to keep this one down, the first one down to 100mm long. Now we will change this further on once we work out what room we have up front and where the balance of the rocket is. So we'll just OK that. Oh, before we OK it, I'll tell you what we can do. We need to change the material again because this will give us our accurate rate. So at the moment, if it was cardboard and it obviously so thin and so small, it's weighing just less than 2 grams. Carbon fibre is obviously an extremely light material, but it's more than twice as heavy, but it's 100 times stronger. Right, so we'll OK that. Next, we need another body tube. As I said before, it'll come a bit more clear in a minute. So again, it's picked up the outer diameter. We need to change the inner diameter, wall thickness, which will change the inner diameter to 18. And again, we'll change the length to 100. Now, what that's given is your two body tubes. So it's giving you an indication, slowly but surely, how the rocket's going to look. Now, because this is an altitude rocket, and I also want to practice making boat tails because they help drag with the aerodynamic drag, bringing the air cleaner out the back of it again, we're going to do what's called a transition. Now, most people, if it's the front of the rocket, will transition from a small one down to a larger body, working the way down. I'll tick the box again. So what we're going to do, we're going to put the length down. Now, we only want a small transition at the end, so we're going to go for 15mm. And at the moment, obviously, we have got the diameters the wrong way around. We want to transition smaller. So we're going to go to after diameter, and we're at 19mm now, and we're going to have about a mil wall. So if we go 17, just have a taper down, that just gives us a slight taper. So that'll leave us with an inner hole of around 15mm. And I'll explain why that's going to be important soon. And again, we need to set the thickness, which we're going to do it the same as the nose cone, so we'll do that at 1mm. And again, we need to change the material type to carbon fibre. And again, we want to show in our Saka the same process. We want the diameters to be 18, we want it to be 5mm inside the rocket, and the thickness again is going to be 1mm. Now this again is giving us our weight or our estimate of what a component will be when it's made. The next thing we need to consider is the motor. Now normally if it was a minimum diameter motor, and this actual rocket itself won't have a sleeve, but limitations with the software means if I just put a motor in, it's going to want to be at the end of the tube here, but we're going to have an internal shoulder which is going to have to stop it here. So what we're going to do is click on the tube that we're working at, and we're going to put an inner tube inside it. Again, it'll, because it's a different part, it's going to come up with that, so we're going to tick it. So now we've got an inner tube in it. So the inner tube, we're going to have this length of the motor. Now the motors we're working with are 18mm by 70, which is the default on this. We've got a wall thickness of 1.5 and it's weighing 1.3 grams. Now because we don't want to cock our simulation up, I'm going to say this weighs 0.5mm thick, which puts the weight down to an absolute minimum. So it's not going to affect anything. Now over on this side where we've got placement, this is what we're going to use to set our motor positioning. So if you look, if we add positive, we can push it out the back. If we have negative, that brings it on the inside. So it's now set to where the motor's going to butt up to the end. There's no relevance in the weight, it's just there to help us set the position of the motor, so when we're working out the centre of pressure and the centre of mass, they'll be in exactly, though the rocket will be balanced and stable, so we can OK that. Now what we need to do before we can really throw any of the fins, before we can work anything else out, there's a couple of things that I want to work out with this rocket. Now at the moment I'm going to install the motor. Now there's 4 motors we're going to use, so I'm going to, well, maybe 3, an A, a B, a C and a D. Each motor in relevance is twice as strong as the next one in theory, so it's significantly heavier. So I'm going to pick the C motor, which is going to be sat in the middle. So what I do now is select the inner tube, which is the inner tube, click new configuration, and this is going to give us a list of every manufacturer's of motors. Now the motor we're going to use is a Klima, and it's going to be the Klima C6 with the 7-second delay. So we'll take that, and now you can see we have the motor installed. If we have a look down here in the bottom corner at the moment, it's only going to go to 5 meters because it's just going to go off like a spinning jenny, which is extremely dangerous. So we need to get some stability in the rocket soon. But before we design our custom fins to go on the back, we have got to get whatever other mass and stuff in the rocket. But first of all, we're just going to adjust the sizes. Now, as I was saying before, the reason that we've got 2 body tubes is because we're going to use the motor itself as a coupler. So once this motor has done its work getting us up there, it's done its 7-second delay, there'll be an explosion out the end of the motor which will throw the end off, which will then pull normally a parachute, but we're going to use a streamer on this example. So what we're going to do is I'm going to reduce the size of this down to 50mm. Now that's set to 50mm. I'm just going to go back to my design and have a look. We're at 105 to 130, so there's 25mm on there. Now I want a little bit more than that, so I'm going to go back to this motor tube itself. So I'll go back to the second tube, and I'm going to put this down to 45mm. Now this is down at 45mm, that's leaving us exactly 30mm for the end cap to go over the end. So this section here now, including the nose cone, is the top that will eject. There's going to be a cord attached between the two, and we get some electronics in. Now the electronics that we need in, we need a flight computer to get our reading so we could submit it for the record, and we also want a device that's going to help us find it. Now it's not a tracking device, it's a screamer. It beeps, it makes noise, so you can find it. Now we need to just check dimensions and weight. So if we have a look, there is a company called Wizard Rockets who's always at the Midlands Rocket Show, which is down in the Midlands at the club once a month. Now the 2 devices that we want is, I think they're around £15 when they're in stock. This is the little device that's basically taken from drones, and what happens is it detects movement, and as your rocket's flying, once it hits the ground, there'll be no movement. After 30 seconds it panics and starts making a noise. The other device is this little flight computer. Now this is what's going to get us the altitude. With this being the heavier of the 2 devices, I want this further up the end of the rocket. Now the reason we're doing that is because we want to offset some of the weight of the motor, just to get ourselves a bit more balance. So we can see here we have the dimensions and the weight. So first of all, we're going to get this device simulated inside. So we're 25mm basically by 15 by 15. So that's easy enough to work out. So what we're going to do is go back to our open rocket. We'll click on the top tube, which is up here, and we're going to add a component mass. Now this component mass is just a representation of the beeping device. So we know it's going to be 6 grams, that's the start. We know it's 25 long by an average of 14, 15, so we'll go with 15. So now we have a look. We can again just creep it a bit up into the nose. So we'll put that roughly where we think it's going to sit. Next of all, we need to go back again to Wizard Rocket and have a look at the next device that we're getting in, which is the little peak altimeter. If we go to the manufacturer's website, I think it's around here somewhere. Yep, here we go. So it is 18 by 14 mil and it's 1.9 gram including the battery, which is absolutely unbelievable for the date that you can pull off. So 18 by 14, we can put that as our next component mass. So we'll get our mass in, and we are length 18, diameter 14, and component mass was basically 2 grams. Now we need to move that back. Right, the only other thing now that we need to go in the rocket is in this section here. We want a streamer. These are going to be protected by wadding. There'll be wadding here, which is like a fireproof, basically toilet roll looking material, and then we need a streamer which is going to be made out of like Maya foil. It basically looks like tin foil, but it's plastic. It's extremely strong unless it's got a nick, and it's highly visible, and with the air flowing over it, we're using it to reduce the weight as much as we're using it for visibility. So looking at this, I'm at 70 to 100, so that's leaving me about 30. Now ideally I'd probably want a 50 mil wide streamer, so we're going to add 20 mil onto this rocket. So we're 120 there. That gives us the extra 20 mil to make that 50 mil with the streamer popped in it. Right, now we're going to add a streamer, so we click on there, we go to streamer, we want the streamer length. I think we'll get away with at least 2 meters, so we'll go 2.5 meters, which is 2,500 mil. Width we want 50 mil, and then pack length. So pack length's going to be 50 mil. Pack diameter, we're going to get it down to 18. We're going to get it in the rocket. Now that has give us a mass. So we need to go to the plastics, change it to the material that we use in Mylar, which massively reduces the weight. And then what we need to do now is use the positioning again. So in theory, this is going to fit inside this little gap. Keep moving, keep moving. There she goes. So that's the basic setup. Now the main thing now, obviously we're at minus 7.9 and minus I think 70.5 stability. This thing has no idea where it wants to go. So we need to add some fins. Now because we've got a slight boat tail on the back, we have to use freeform. Now the type of fin I'm going for is like a delta wing, a clipped delta, which means basically a triangle with the end cut off, and then we're also going to do it swept, a bit like a fighter jet wing. So we'll go to freeform. Now as you can see, the model below has thrown the fins on. So here is the amount of fins. If we went 4 fins, that's how it'd look. If we did 3 fins, is how we're going to do it, because we want less drag. So first of all, we're going to put the 3 fins on. Now we're going to use carbon fibre, and we're going to cut these out of flat carbon fibre sheet. So these are going to be 0.5 mil thick. So we'll put our 0.5 in. We make sure that we change it to the right material, and it's composite carbon fibre. Gives us our weight. Now at the moment we've got a stability of 2.68, 21.7. This rocket, stable rocket, about 10% stability, is going to be around 1 cal. Now I'll do another video at some stage to explain it, but basically your cal is the distance between these 2 points. Your centre of gravity, which is where if you put your finger on it, it'd be like a scale, it'd be balanced. And then you've got the centre of pressure, is where the aerodynamics and the field and the pressure of the air coming over, that's where the centre of pressure is. Now for a rocket to fly stable, the centre of pressure to the centre of gravity to the centre of pressure has to be greater than the diameter of the rocket, and that's how you get these cals calculated. So in theory, that's 2.6 times basically what the diameter of my rocket is, if I'm correct, but feel free to quote if I'm wrong. But the computer doesn't lie, so we'll use the computer. So what we need to do is we're going to reduce these fins because we don't need the amount of drag that they're going to do, and we want to get as close to, with this kind of rocket, 1 cal as possible. So at the moment we have got 50 centimetres of base. Now we need a good root cord to stick it down, but I'm pretty sure 3 is going to be more than capable of this. So we're going to drag it in a few centimetres. There we go. And also, we don't want the fins sticking over the back of the rocket, and they're extremely sticking out. So what we're going to do, we're going to drag 1 in and down. Still at 3.16 cal, but a very weak tail. Right, so now let's imagine that was our triangle. We're going to delta clip the wing, and we're going to sweep it slightly. Now we're at 1.5 cals. Now with a lighter motor, we're going to be nearly 2 cal. So we want a happy medium. I think we'll bring the nose down slightly, bring it back. Let's get this looking a bit better and a bit sleeker. I think that's starting to get there, but we're a little bit low on the cowl, so we're just going to give it a little bit more fin. 1.2, and then we just want what we got now. We're going to need a little bit more root cord, so we'll get a bit more that's going to be stuck down just to give us that bit more strength. So we'll take the fins back slightly, so if it does land, it's landing on the back of the carbon fibre rocket and not onto the fins when it hits the ground. We'll try and take a little bit of that away from it and not go for the sweep. Right, there we go. So that's our basic rocket design now. What I'm going to do to get the fins away from the end can a little bit more. Again, you've got general and you've got positioning. So I'm going to bring a couple of mil from the end, just so if it hits the ground hard, hopefully the bottom bit will take most of the shock out of it. And we've got our stability. Now, by the time this motor burns a little bit, it's going to lose weight. We're going to get more and more stability. So I'm more than happy with that. Again, it's my opinion, but I'm more than happy. So basically, this is the design of rocket that we've got. So what we can do now, before we do any simulations, we can get the other motors in. So we want one with the Klima C6, which is a C-class motor. We're going to put the B version in, which is half the power. And we'll also do a D, and we want a D9, which is the biggest one that they do, in an 18mm, and okay that. Now, so if we have a look now, we've got our motors here. So we'll have a look at B. Now, what we're aiming for here at the moment with the B. Oh, we've got a B0, bear me 1 second. I have not got the right delay timer in. 4 seconds, that's the maximum. Right, that makes more sense. Now, when we look down here in the bottom left of the screen, it basically says apogee, which is our maximum height, is 341 metres. So we want to have a look now at the UK record. Now, to get the vacant UK record, because it's all been redone, you've got to beat 253 metres. So let's have a look what we're achieving here. Almost 100 metres, 300 foot above. Easy. not a problem. So we'll go to C. Let's have a look at the C class. C class 453 meters, 662. This is sounding far too easy. Let's have a look at the D. D, we're capable of 1,025 meters, which is over 3,000 foot, and we're absolutely smashing it. So, is it going to be this easy? Well, no. And if you watch the next video, you'll find out why this project might be dead in the water before I even started. Before I go, we'll just have a quick look over the rocket in an unfinished view to give you an idea of what the mass and load will be and the idea of the rocket. Have a great evening, and I'll see you in the next video. Hopefully we'll have figured out the problems and we'll move on to actually prototyping and designing the rocket using fully 3D printed parts. Thank you.